as I'm doing. So the coefficient of determination sounds tricky. We've done the correlation coefficient, but it's not that bad. We've got a fair bit to go through, but you're going to see it's actually pretty easy. So the coefficient of determination tells you, it gives you an indication of the degree that two variables are linked, the degree or the level of relationship between two variables. And it's used, and I personally think this is a loose association, but it is used in a way such that you can give a percentage association. So once we determine the coefficient of determination, and it's 0.95, some people would say that means they're 95% connected. Now, mathematically, in the build-up of the formula, I don't really agree that that's a perfect statement, but that's what you are allowed to do. The coefficient of determination is R squared, capital R. And you've probably played with this before if you've done any linear modelling stuff and you've seen it on Excel or something like that. You can get your R squared value. You do that a lot with linear modelling in science. R squared is just the square of little r, and little r is your correlation coefficient. So what do you need to know for today's lesson? If you need to work out the coefficient of determination, you just have to get your correlation coefficient and square it. That's it. So really the hardest thing from today's lesson is making sure that you don't confuse correlation coefficient and coefficient of determination. They're the two things. Here's an example. The correlation between weight and height is 0.8. There's no more context than that. What is the coefficient of determination? Anybody know? .64, perfect. So 0.8 squared. And so the statement here would be there's a 64% connection between those two variables. Now, your R value is always between -1 and 1. What the correlation of determination does is it makes the negative values positive. So you lose that opportunity to talk about whether they're negatively connected or positively connected. I've got that back to front for you guys. Positively or negatively connected. But it gives you that percentage opportunity which you're allowed to do. It also takes a number below 1 and makes it smaller. So it actually probably decreases how linked data is. So just keep that in mind as well. 0.64 came from 0.8 as an R value. So there's still a fairly significant connection there between the variables. And so you can say that's 64% connected. We'll get to that. Interpreting. So the percentage tells us the variation of the response that's explained by the explanatory variable. That's what we can say. So this 64% of, I don't know which one was which, but the weight outcomes can be explained by the height. That's the statement you can make. 64% of the variation in people's weights is explained by the variation in their heights. So this is going to be key. You're going to be asked to describe two data sets using the correlation of determination. And to do that, you will just get the percentage of your R squared, turn into percentage, and then you'll make a statement. 64% of the variation this is the response variable, can be explained by the variation in the explanatory variable. So don't forget we have to get that response and explanatory variable right as well. And so this is, and you'll see in this last bit here, 36% can be explained by something else, which is what we expect. There's not many things that can be perfectly explained by one variable, but you know that have to be perfectly linear. So, for example, maybe the cost of a taxi ride based on how many kilometres you travelled, that might be explained perfectly. So, just a couple of examples. For the relationship described by the scatter plot there, the coefficient of determination is 0.5210. Determine the value of the correlation coefficient, R. Does anybody know the value of R here? Any takers? I'll take that, 0.7218. So actually I won't take that exactly. I'm going to say it's the square root of R squared. So the correlation coefficient is the square root of the correlation of determination. So in this case, it's the square root of 0.521. Get about the 0 on the end. And that's 0.7218 is our R value. Is that the right answer? That's my next question. So, negative. Why do you say negative? Don't forget, if you're taking the square root of a number, say for example an easy number, you're taking the square root of 9, but another number could also square to give 9, and that's negative 3. So when you take a square negative or positive, and this is where we have to go back to the graph and say it's negative correlation. So you can see that negative correlation there, and therefore R is equal to negative 0.7218. So this is an easy calculation. This is just a little bit of analysis at the end that you have to make sure that you do. So just be careful with that. Type of thing they might put in as a trick question for you. Any questions? A couple more really easy examples. Carbon monoxide, CO2 levels in the air, and traffic volume are linearly related. So that is the amount of carbon monoxide in the air against traffic. Which one do you think is the explanatory variable? I can't. Did you see what I just did then? Can you see what I just did then? It's written here. So I just tried to cover it up on my screen here. That's good. I had a lecturer who tried to spot a fly off an overhead projector once, but he had the overhead projector here, projecting up on the board there, and the fly flew onto the overhead projector and he tried to spot it on the board. It was great. Anyway, side story. So the traffic volume is explanatory. Take a second to think about the context. We don't expect you to really know a lot about context. That's not an expectation. But if you know enough about this to say, is it more traffic increases the CO2 level? Or is it if I go out there with a bottle of CO2 and spray it on the road, traffic will appear? Which one's it going to be? And the answer is obviously going to be that more traffic is going to increase the CO2. So you've got to be thinking about that a little bit as well. You'll see here that sometimes, and the textbook does this, it won't just be R. You'd like it to just be R, that's easy to spot, but they've said R of the response variable, comma, explain. You might see that sometimes. It just looks a bit more confusing, but it means the same thing. So we're told the R value, determine the value of the coefficient of determination. So R squared will be equal to little r squared, which is 0.985 squared. This is really, really tightly linked. I don't know whether this is true data, but it's really, and when I square that, I get 0.97. I'll just leave it as 97. 9702 is probably better. Any questions on that? The actual maths in this topic is pretty easy. Just got to get those little tiny contextual things right. I think there's only one more. Scores on tests of verbal and mathematical ability are linearly related with that. So is this strong correlation? Not really. In fact, if you go back to the zones that we talked about last lesson, which are pretty loosely linked zones, this falls into the second zone, that R value. So we would say that's weakly related. So it's a weak correlation. Just a bit more than that 25% mark. So that's the R mathematical to verbal. So we're saying here that the explanatory variable is the verbal result, and that your mathematical ability is based on whether you've got good verbal testing. And my R squared value is R squared, which is 0.275 squared, and 0.0756, which is a fairly low R squared value. And the claim here is that 7.5% of your mathematical ability can be explained by your. That's the claim. So you can then make that statement if you need to. So write it in terms of percentages and interpret. So this is equal to 7.5% of mathematical ability can be explained by verbal. Opportunity to ask questions.